In the previous video, we took a look at being able to plot the area that was bound by a function in the x-axis. And to be able to evaluate that area, we can use a definite integral. And so in this video, what we're going to do is we're going to take a look and see how we can use MATLAB to evaluate our definite integrals. And we're going to take a look and see if we can get both the exact as well as the approximate solutions to those areas. And so let's say we have a symbolic variable x. We could use this function int f comma x comma a comma b, where f is the function, x is the variable of interest that we're integrating with respect to, a is the lower bound, and b is the upper bound of our definite integral. So to be able to evaluate something like this, 1 to e of ln x dx, we can just use a Sims variable or symbolic variable x. We define f to be the natural log, and then we use this function int f comma x comma 1 comma exp1, because e is really e to the first. So let's go ahead and take a look and see how we can use MATLAB to evaluate these definite integrals, and we're going to give the solution both approximate and exact when possible. All right, so we're going to start out with a symbolic variable. All right, and then from there, what we're going to do is define the function. So our function f is expx plus a sine of x. We're going to integrate, and I'm just going to call that answer 1 is going to be equal to int of f comma x comma 0 comma 1/2. To be able to get the output, what I'm going to do is I'm going to make an fprintf statement. So I'm going to say fprintf, and what we're going to do is we're going to say that the approximate answer is, and you might remember from our first section, %.6f rounds to 6 decimal places. And I'm going to use a /n. All right, make sure you don't use this \n. Make sure you use /n. Okay, so make sure it goes from top to bottom diagonally, and then accent. And then the variable that we're trying to get the answer for is answer 1. Right. Now I'm just going to execute this just to show you what happens, and then we'll do the other ones, and as well as the precise answer or the analytic answer. And this is our approximate answer. If we want to get the exact answer, we can use an fprintf statement. So we're going to say fprintf, we can say the exact solution is, and I'm going to use %s this time, /n. And I'm going to call answer 1. Right. %s is string, so that means it's just going to read it as a character, not as, or characters, not numbers. All right. So if I execute it, right, we get the precise answer. Okay. So this is what you would get if you were to do the problem by hand and to use our techniques of integration and use the fundamental theorem of calculus. Okay. Of course, if we want to, we can just label this as problem 2b. Now, what we're going to do is we're just going to copy and paste this code. Sorry, this is 2a. And all we're going to do is just redefine each of the functions and the bounds each time. And we can just go ahead and just use the same code over. Right? So for our function this time, we're going to have log of x plus 1 plus x raised to the 1/4 power, and then plus 1/5 times x cubed. Note that we're not putting the periods here and here and here because we're dealing with a symbolic variable and we haven't defined a row vector. Right? Remember last time we did that, so we don't necessarily need that. It won't do anything bad, or it won't do anything to prohibit you from getting the answer, but no need to do it if we don't have to. We're going to change the bound to 0 to 1, and the rest of it should be the same. Let's just call this answer 2, just so we can differentiate from answer 1 and answer 2. Right. I'm going to go ahead and run. Right. And here we go. It gives us both the exact answer and the approximate answer. And if we want to, we can even go further. We could say the approximate answer to problem 1 is, and we can just go ahead and just kind of insert that. So that way, if we're reading these in a line, we know which one's which. All right, and the approximate answer to problem 2 is, and the exact solution to problem 2 is. All right, and once again, we can just cut and paste this code and just change a few things. All right, so I'm going to change this to problem 2C. This time we have tan x, sine x, pi fourths to pi thirds. So we're going to change the function accordingly. This is going to be our tan of x plus sine of x. We're going to change the bounds. I'm going to change this to answer 3. And that's going to be int of f comma x comma pi over 4, pi over 3. And we can just change this to answer to problem 3. Change this to answer 3, change this to answer 3, and problem 3. All right, so we're going to run one last time. All right, and it gives us the approximate answer to all 3 of the problems, and it gives us the exact answer to all 3 of the problems. If you want to put a space in between each of these, what you can do is you could do one more f print f line, and you could just do \n and then close it out. All right, and what that'll do is that'll just make a space or like a return key in between each of those if you want to. All right, and just for good coding practice, I'll go ahead and put one at the end so that way it's a little more legible. And there we go. All right, so that way it looks a little bit better as the output line. Okay, so that's how we can use MATLAB to be able to evaluate definite integrals. And you might remember what these represent. These are the approximate solutions to each of the areas that we graphed in the previous problem. So remember up here, we graphed each of these and we labeled the axes. And now what we were able to do was to be able to get that area that was bound for each of those. So now we have a geometric representation, we have the approximation, and then we also have the analytic solution to each of these. So in the final video, what we're going to do is we're going to take a look and see how we can use MATLAB to evaluate indefinite integrals.